Have you ever stopped to think about how we get these incredibly complex machines, computers, to do exactly what we want? It's kind of a wild thought, right? We speak in languages like English, but they speak in the language of pure electricity. Today, we're going to unravel that mystery. How in the world do we talk to machines?
So that's the central problem, isn't it? You've got us on one side with all our complex thoughts and messy human languages, and then you've got computers on the other with their super rigid logical systems. So how do you possibly bridge that gap? How does that conversation even happen? All right, let's really dig into this. Because before we can talk about the solution, we have to appreciate just how big the problem is. We're talking about a massive communication barrier. It's like two beings from different universes trying to have a chat.
Think about how we operate. Our minds work in abstractions, in nuance, with layers of meaning. Our languages are full of context and emotion. It's how we write poetry or just, tell a joke.
But a computer doesn't get any of that. It's not abstract, it's brutally literal. Its entire world is built on something far more basic and honestly, way simpler than our own.
So, let's pull back the curtain for a second. Let's look at this from the computer's side. What is the one and only language that every single computer on the planet understands at its absolute core?
It all comes down to one thing: binary. That's it. It's a language with just two letters, 0 and 1. And these aren't just abstract symbols. They represent something real. A 0 means an electrical signal is off. A 1 means it's on. That's all the computer knows, on or off.
So you might think, well, why don't we just learn binary? No. Can you imagine trying to write a book or even just an email using only zeros and ones? It would be basically impossible for a human brain to handle that level of mind-numbing detail. We needed a better way.
So if we can't speak binary, and computers definitely can't understand English, we're stuck. We need something to stand in the middle, to act as a go-between. We need a bridge between our world of ideas and their world of circuits. And that brings us to our essential translator.
And that bridge is what we call a programming language. The best way to think about it is like a special shared rulebook. It's got its own vocabulary, its own grammar, its own set of symbols that lets us write down what we want the computer to do in a way that we can actually read and make sense of.
And here it is. This is the aha moment right here. On the left, you see a super simple command in a language called Python. Even if you've never coded, you can guess what print hello world does. And on the right, that's the exact same instruction in the sea of ones and zeros the computer actually understands. The programming language is the magic that does that translation for us.
Okay, so we know what a programming language is. It's the translator. But how does that translation actually happen? How does that simple line of text we wrote actually become an action the computer carries out? Let's follow the journey.
It's really a pretty straightforward three-step process. First, a person, a programmer, writes the code. Easy enough. Then, and this is the key part, a special program called a compiler or an interpreter acts as our translator. It reads our human-friendly code and turns it into that binary machine code. And finally, the computer's brain, the CPU, just takes that machine code and does exactly what it says.
Now, it's important to know that not all languages are the same. We generally group them into levels. You've got your high-level languages, like Python, which are designed to be closer to how we talk. They're much easier to learn and use. Then you have low-level languages, like C, which are way closer to the machine's own language. And here's the trade-off. High-level is all about convenience for us humans, while low-level is all about raw speed and performance for the machine.
Okay, so this brings up a pretty logical question. If all these languages are just translators, why on earth are there so many of them? Why not just pick the best one and use it for everything?
Well, the answer is specialization. Think of programming languages like a carpenter's toolbox. You wouldn't use a saw to hammer a nail, right? It's the same idea here. Different languages are just better suited for different jobs. For example, Python is the go-to for AI and data science. JavaScript pretty much runs the entire interactive web. And if you want to build a high-performance video game, you're going to reach for a powerhouse like C++. It's all about picking the right tool for the job. So, if you're going to take one thing away from all of this, let it be this idea right here. A programming language isn't just a bunch of weird syntax, it's a bridge. It's that vital, incredible link that connects the abstract, messy, creative world of human thought to the cold, hard, logical world of computer execution. Without that bridge, our modern world just wouldn't exist. And that leaves us with a pretty cool, provocative thought to end on. If a programming language is the fundamental tool we use to build entire digital worlds from scratch, to create everything from our social networks to the software that flies spaceships,
What are we going to decide to build next?